Hello guys and welcome to my channel. Today we're going over a project that me and my team did for our ECN 361 class. It's a golf ball finding robot, and there are two big problems that had to be tackled with this project. Number one was training a machine learning algorithm to identify the position of a golf ball so that the robot could navigate to its location and collect it, and the second part was the hardware side of things and building a robot that could collect golf balls. What you're looking at right now is the machine learning algorithm that was used to train the model, and here we have a whole lot of images of golf balls or not golf balls on the golfing green. This model was built using the TensorFlow Keras library, as you can see right here. It's a very powerful library at making the TensorFlow package easier to use and understand. We start out by loading each of the images in one at a time, resizing them to make it easier on our computer. Originally, this project was designed to be run on a Raspberry Pi, so the lighter the better. However, because of some problems with importing the necessary packages, including TensorFlow, we ended up running it from a computer and following the robot along as it collected golf balls. We can see right here we also had an array of the positions of the golf balls. We did create a program in JavaScript so that you could just cycle through all the images really quick and click on the golf balls. If there wasn't a golf ball in the image, you could simply hit the space key and it would log a 0, and then we can load that array as our targets data set. We split the targets 2080, and then we normalize everything and begin training. We used convolutional 2D neural network to train this algorithm, and we set it through its paces many times, trying to dial in the best model to use. You can see here that as we go through each of the epochs that, or epochs I guess, depending on how you say it, as we go through them, we're collecting this history of not only the training, accuracy, and loss. You can, of course, log it into the history right here. And, of course, you could run that through multiple epochs at the same time, or epochs again. But the issue with that was you can't exactly, as far as I'm aware, take a history of the accuracy and loss against the validation set. So that's what this whole for loops for. By running it in debug mode, we could break out at any desired point. If we saw signs of overfitting occurring, we could simply break out and have the perfect model, or the most ideal model given the data and the model design we were using. Here we have the actual program that was supposed to run on the Raspberry Pi and ended up being run on a computer. You can see here that we start up a camera to capture images, and then we also start up a serial port to communicate with the Arduino. We wait for the Arduino to start that communication, and then it's sort of a pooling process where the Arduino can request from the Raspberry Pi to go out and see if it can find any golf balls. It then goes through this loop to collect 3 images and make 3 predictions on those 3 images, which are stored in samples. Right here you can see that happening. At that point we do a triple modular redundancy test to see if 2 of those 3 samples contain the same value. The problem we had predicted encountering was that our model only could predict on a validation set with 86% accuracy. So this was to help mitigate the effects of that. We didn't want the robot running off after a golf ball that did not exist. So it would test against 2 of its 3 samples, and if 2 of those 3 samples came out the same, it would give that more attention, and if every sample was unique, then it would ignore it and just continue going straight. And here you can see a history of our training. across 40 to 45 epochs. Originally on the hardware side, we started with this design which used gears, and you can't see them there, they were inserted after the fact, but steel wires to move the ball up along a tram and into a carriage. Later on, we switched to this new design that would rather use a belt with arms attached to steer the ball up the ramp and into the carriage. Here we have the Arduino code. As you can see here, we set up a connection with the computer and initialize that communication with first character. We also set the pin mode of our treads. They were designed to be able to go either forwards or backwards, but we're just using forwards in this project. Regardless, we do have to set them up with initial values. After we've received a response from our computer with the location of a golf ball, if there is one, it gets mapped to a character. A is 0, F is 5 or hard right, and between that you of course have a soft left or a hard left, straight, soft right or hard right. Here we take the response from the computer or the machine learning algorithm, and we can adjust the speed of either the left or the right tread depending on the response that we get, and then we turn on that conveyor belt if a ball has been detected. Here you can see the robot with that tram I mentioned earlier on the side, all 3D printed and ready to go, with a cardboard carriage to hold all the balls collected. As it gets started here, you'll see that conveyor belt start up right away, and there's a little pusher on the front to get it into that tram. Unfortunately, the motor jams a lot and it needs a little bit of help, but once you get it going, it worked. In this clip, you'll notice that the tram does not start immediately. This is because it's designed to only start once it finds a ball. You'll also notice that the ball didn't make it in the tram. We realized that the robot went a little bit too fast, and oftentimes it would knock the ball out of the way. That was obviously something we could have fixed with more tuning and may do in the future. As you watch the lower left side of this screen, you'll see the robot pulling its 3 coordinates, and as the golf ball comes into view, detect it so it can pick it up.